Now, last time I mentioned to you about how the entire discovery of the fission process actually happened. And basically, what they found is that when it breaks up into two of these fragments, then the total, and if you look at the highest known isotopes of these elements which were known, like barium and krypton, it was not possible to really accommodate all the neutrons which were originally present in the uranium. Okay, so at that point, it was realized that some neutrons have got to be released in this fission process, and the number of neutrons that are released is more than the number of neutrons that you put in. So, for example, I am taking one neutron, and here is my uranium-235. This is the fissile material. Uranium-238 is not fissile. Okay, so this is the one, right, which is being bombarded, and it's splitting up, and one is going to krypton, the other is going to barium, all right, and these are the highest known isotopes, of barium and krypton. And what it meant is that 3 neutrons are now getting released, and now 3 can in turn now go and strike 3 of these, and so you will have a continuous multiplication of the number, right? And so that is what is a chain reaction. Of course, you can have controlled chain reaction and uncontrolled chain reaction. Like in these particular cases for nuclear power, typically they will not allow more than 3 neutrons at most, to get formed, because otherwise it will get uncontrolled. And that also, the number of neutrons have to be controlled. Some of them will be destroyed, just so that things don't go out of hand. Whereas if you're making an atom bomb, then of course you just allow them to multiply as much as they want, just so that you have the maximum impact of the bomb. Okay, so that's really the main difference. Now, after the this discovery, 19 as I told you, 1938-39 was when it was discovered, and then around 1944 the weapons went off. But then after that, people started thinking in greater, with greater sanity, and this is actually a very important pocket book, which was released around 1945, and I'll just read out just so that you know. In August 1945, the first widely distributed account of nuclear energy in the form of the pocket book, The Atomic Age, discussed the peaceful future uses of nuclear energy and depicted a future where fossil fuels would go unused. Glenn Seaborg is quoted as saying, "There will be nuclear-powered Earth-to-Moon shuttles, nuclear-powered artificial hearts." Eugene Wigner and Alvin Weinberg also took out a patent on a conceptual design of the first light water reactor. Okay, that's the US patent number. I'll send it. I don't think you'll probably have the patience to read it, but for your records, I'll send it. And if anyone is interested, you can go ahead. I mean, so the design was made long before the reactor actually was made. Okay, but at that time itself, they had conceived that it will give limitless power. And that would later become the United States primary reactor for naval propulsion. And I showed you those submarines, and that was the naval propulsion that they are talking about, and later take up the maximum share of the commercial fission electric power plants. All right. And as I mentioned to you, roughly about 25% of the power in the United States is generated from nuclear energy, and in France it's close to about 72%. So I mean, but then there are many countries now who have also decided to opt out. Now, so let us quickly again recap then how a nuclear reactor works. So uranium-235 fission, produces around 3 neutrons, and each of these can initiate more fission. Okay, and that's how you get a chain reaction. And the system is set up so that if you feel that it is getting uncontrolled, you can control it. All right. Uh, then in this, normal water, just H2O, is used as a moderator to slow the neutrons. Why to slow it? As I think we had discussed last time, that fast neutrons don't interact very well with the nucleus, of uranium-235. So you need to slow it down, right? And water is a very good way of slowing down the neutrons. Okay, so that's effectively what water does. It not only slows down the neutron, it also absorbs all the energy which is being created from fission, and that's how steam is generated. Okay, so water plays more than one role. Okay, and so what happens to those neutrons which are absorbed by the water? They actually become deuterons. That's in a way a good thing. It's also a good way of making deuterium, which is actually very useful. We'll talk about the role of deuterium. All right. Now, what happens is that the normal percentage of uranium-235, the fissile material, is about 0.7% in natural grade uranium. Okay, but under those conditions, if you use normal water, it is not possible to sustain a chain reaction. Okay, what has been found is that you typically need to increase the concentration of uranium-235 from 0.7% to around 2 to 5%, somewhere in that range. Okay, and so that is really the fuel that, for example, in all the reactors in India, that's what we use. We use a partly enriched uranium. Okay, if, for example, things are getting uncontrolled, right? If there is excessive amount of neutrons being produced for some reason, there are certain rods, which are made of boron, and boron has the ability of absorbing the neutron. So it absorbs the neutron and cuts off the further reaction. Okay, so you can effectively, if you need to shut down, for example, the reactor for some reason, if it is going out of control, I mean, you can insert boron rods. Okay, and they will mop up the neutrons, and the reactor will basically cease operation. Okay, so just remember that. And the hot water is boiled, the same water which you are using as a moderator. Okay, that hot, so moderator moderates the velocity of the neutron. Some amount of course gets converted into deuterium. Okay, but for the most part, the moderator effectively just slows it down. And whereas boron absorbs it. Okay, and this water of course gets heated and it starts boiling. Okay, generates steam. Okay, and that's how you run a turbine, and the rest of it is identical to normal ways of generating power. There's nothing different. Okay, so you can see, I mean, this is the a slow neutron which goes and strikes the uranium 235. Okay, and so this is your uranium 235. Now it strikes as slow, but what comes out is fast. Okay, these are fast neutrons. So now you've got water here. Okay, and water is basically slowing down the neutron. Okay, so it slows it down, right, so that it can be again captured by another uranium 235. Okay, so that's how the multiplication is happening. You can see from 1 you have now done 2, then you increase it to 4. Okay, and that's how you are every time it's doing this, it is multiplying the number of fissions that you're carrying out per second. Water slows down the neutrons, plus at the same time it also mops up the heat, and gradually becomes steam. Okay, and that's how you generate thermal energy, and from that you run the turbine. You get steam and you can run turbines. Okay, so this whole process of basically slow, fast comes out, again slow it down, again it reacts, etc. That's what is shown. Now, and then I mentioned to you that if you are using water basically, even though of course it slows it down, but as I told you, some amount of the neutrons also get absorbed by the water. It forms deuterium. Okay, and so you will not be able to sustain a chain reaction. Okay, if you just use normal H2O. Okay, and so that's the problem with simple water. And but on the other hand, if you use deuterium, if you use D2O, okay, or HDO, okay, then these things are much better, okay, at effectively slowing down the neutron but not capturing the neutron. And so what happens is that I don't need to enrich the uranium. In the regular water, boiling water reactors, I need to enrich uranium from something like 0.7% by weight to about 3 to 5% by weight. But if I were to use a deuterated water, then I don't need to do it because there's no loss of neutron. Okay, so I'll just quickly read out what is written here. Neutrons need to be slowed down to induce fission of uranium 235. This is done well by water. However, light water absorbs some of the neutrons in the process, whereas heavy water only slows down the neutrons without absorbing these. The greater concentration of slow neutrons in the case of heavy water as moderator enables naturally occurring uranium to achieve criticality. Okay, criticality means something that can sustain a chain reaction with heavy water as moderator. Now, this concept was exploited for the first time by the Canadians. Okay, and they are the ones who put up what is known as the CANDU reactor, means Canadian deuterium based reactor. Okay, and and the beauty is they don't need to enrich the uranium, okay, in this reactor. So it's wonderful. Okay, on the other hand, when light water is used, 4 to 5 fold enrichment of uranium 235 is essential. Okay, so there are two things that we will discuss as we go along. One is that I need to enrich the uranium 235. Now the rest of it is of course uranium 238. Now uranium 238 as such doesn't undergo fission. Okay, but it can have a nuisance value. Okay, in the sense that it can also absorb some of the neutrons and therefore cut off the process. And so one has to look at the basic job and what to do with the uranium 238 very carefully. Okay, now let us these are not all the types of nuclear reactors. Okay, there are more, but I'll tell you the ones which are relatively more popular. One is known as the pressurized water reactor. Okay, now these first two, they just use H2O, light water. Okay, and you can see CANDU, Canadian Deuterium reactor, it uses heavy water. Okay, and in these you can see the uranium has been enriched to about 3% or thereabouts, and in this particular case you just use the natural grade 0.7% uranium. So that's a huge advantage. Now, in the boiling water reactor, okay, what you do is that you have only one type of water, H2O, and so it is acting as a moderator, slowing down the neutrons. Plus, as I told you, it's becoming steam. Now, the pressure of the reactor is around 1050 psi. So you can work out, if you divide that by 14 pounds per square inch, you'll know how many bars it is. Okay, and you can also see the temperature. Right, so this is the kind of pressure and temperature at which steam is being generated, okay, in the boiling water reactor. So obviously, as you pressurize something, naturally the water will boil at a higher temperature, and that's effectively what happens. Now, in this particular case, for example, in the pressurized water reactor, you actually have a much higher pressure, than this, and here you can reach a temperature of around 320 degrees, in as the outlet temperature of the steam. Now, here what one does is that when it is pressurized, in this pressurized water reactor, uh, you have two types of water. One is that you have the water which is enclosed along with your nuclear fuel, and outside of that you have also water, okay, and that water is basically heat exchanging with the water inside the reactor, okay, and that is the water that is becoming steam. Okay. Now, the advantage is that because there is a barrier, there are two kinds of water. One is the water inside the reactor, the other is the water outside, and it is the outside which is becoming steam through heat exchange. That water is not, that steam is not radioactive. Okay. Whereas here, because this water is constantly in touch with this uranium rods, okay, so there can be traces of radioactivity which can be present in the water, which is actually going into the turbine. Okay, so you need some special kind of radioactive shielding, in the boiling water reactor as compared to the pressurized water reactor. Okay? In the CANDU reactor, just like number one, just like this, you have a separate circuit for the steam generation. That is with water. That is not with deuterium. Okay, the D2O part is the one which is actually in intimate contact with your nuclear fuel. Okay, the other part is just regular standard H2O. Okay, and so that's what it is. Obviously, this has got significantly better safety features because you're not having to enrich the uranium. But on the other hand, where will you get deuterium from? Okay, you can do experiments and studies, but we will try and understand a bit about deuterium. Okay. Okay. Now, if you look at typically, what happens to steam, all right, and at different pressures. So this is the steam chart, means the pressure at which water will boil. Okay. So if you are, for example, reaching about 305, 315 degrees, obviously, what it will mean is that this pressure will be much higher, which is the reason why the pressurized water reactor operates at a higher pressure. Okay, so naturally the pressure and temperature are correlated. Okay, in when you are producing steam from water under atmospheric pressure, which is 1 bar pressure, as we know, effectively the boiling point is 100 degrees centigrade. Okay, that's close to over here. You can see. So we are here about yeah. This is in bar. Okay, this gauge pressure. This is not the actual pressure. Okay, this is a gauge pressure. Your actual gauge pressure is equal to your atmospheric pressure plus the pressure of the gauge. Okay, so when it's 0, it means the atmospheric pressure is 1. Okay, so here you can see is boiling at 100 degrees centigrade. And as I increase the pressure, the temperature of the steam goes up. Okay, so that is the standard steam chart. Okay.
I want to ask what is meant by enrichment of uranium?
Yeah, okay, very good. By enrichment of uranium, we mean that you are increasing the percentage of uranium 235. Okay, the two standard uranium isotopes are 235 and 238. Okay, the bulk of it is uranium 238. All right. But the fissile material, the material that fragments into two, the uranium, is uranium-235. Okay, so when you say enrichment of uranium, what you have to do is you have to increase the percentage of uranium-235. All right. Now, I am not even going into how that enrichment is done. Does anyone know? Have you heard of how enrichment is done? Any idea? What is different between the two?
Number of
What is,
electrons.
atomic
What
mass.
number of
Right. So now what happens is that, if you see the diffusion rates of atoms and molecules is dependent on the atomic mass, okay, or the molecular mass. So if I've got something which is heavier, it will diffuse more slowly, and if I've got something which is lighter, it will diffuse faster. Okay. Now, what is done, and many times you read in the newspaper that Iran is doing this, they're building a gas centrifuge, and the US has opposed it, or something like that. Every now and then there is something in the newspaper. Okay. Now, what basically is done is that uranium has a very volatile compound, which is uranium hexafluoride, UF6. Okay, so effectively what you do is that you convert that uranium into uranium hexafluoride. So now you have got uranium-235 hexafluoride and uranium-238 hexafluoride. Okay, and one of them is slightly heavier than the other, and therefore the diffusion kinetics, the diffusion rate, is different for the two. So in a gas centrifuge, just like we can centrifuge liquids, okay. Similarly, you can also centrifuge gases, okay. And so effectively, what will happen is the heavier thing will come down, and the lighter thing will stay up, okay. Then again you fractionate it further. Again, the next time the same thing will happen, okay. And that's how you can enrich, okay, one fraction in uranium-235. Is that clear? Everybody understood?
Yes, sir.
Okay. And that's not the only method. There are other methods which people are working on, but we are not going into that. Now, I told you about the Canadian reactor design, CANDU, all right? But as we said, you need deuterium for that. Now, India is one of the largest suppliers of heavy water. India has developed excellent technology, okay, over the years in being able to get deuterated water, and just so that you understand how complex a task it is. Like if you take normal water or you take seawater, okay, out of every 3,200 molecules, only one is H2O. Okay, I hope you can understand, right? How small it is. It's not even 0.1%. It's less than that. Okay, so now, and that is what you need to enrich. All right. Now, the way you see, this is a very interesting property, right? Like I've just tried to put down the properties of D2O, HDO, and H2O. Okay, H2O, we know that the boiling point is 100 degrees centigrade, right? At 1 atmosphere pressure. Okay, now HDO has a boiling point of 100.7 degrees centigrade. It's not 100 degrees centigrade. Okay, and D2O has got 101.4 degrees centigrade. So if you can continuously do a fractional distillation, so you distill, you condense, the condensate will have a little more, of the or the bottom part, maybe a little more of the H2 HDO, okay, and so obviously the H2O will boil off first, so you collect it, and what I get at the bottom will have a little more of HDO. Again, I do a fractional distillation, and so I can. It's like doing a reflux business. Okay, and like that, I can continuously enrich, all right, HDO. And India has mastered this art of producing heavy water. And so we have a board in India. It's known as the Heavy Water Board. Is it clear to everyone that the boiling points are not the same for
Yes,
H2O,
sir.
HBO, and D2O? Okay, and that is the basis for enrichment. Okay, so again, putting it pictorially, nothing different. Your heat source means your nuclear reactor, right? That's all you have, right? And and you're generating steam that is running the turbine, and then you are having a condenser, so that the water is again condensing, it is getting pumped back, right? And the steam is effectively running the turbine and generating power. Okay. Now, the other thing which I mentioned to you, that where I have a pressurized reactor, a pressurized reactor with two circuits, one circuit is basically the one which is inside the reactor along with my nuclear rods, the nuclear fuel. Okay, so these are the ones where your fission is taking place, is generating enormous amounts of heat. Okay, and then steam is getting generated, but it cannot actually break out from here. Okay, what happens is that it transfers the heat across this boundary. Okay, so blue is less temperature, red is high temperature. Okay, and so from here the steam is coming out, which is a different circuit. Okay, and running the turbine, and in the process, of course, the steam is getting condensed, it's cooling down. Okay, and then again being fed back into the reactor. Okay, so effectively that's what happens. Now, remember another thing, that in all of these things there's also an input of energy. Okay, like for example, I have to run pumps have to it costs energy, no, to run a pump. Okay, so obviously I'll have to look at how much energy am I producing and how much energy am I actually consuming in the process. Okay, and that ratio is the energy output to input ratio. How much is my input energies? Okay, and how much is my output? And in a nuclear reactor, it is as high as 20:1, and that's what makes it so attractive. Okay, you're generating far more energy in the process than what you are consuming for things like running pumps, etc. Okay, so please keep that in mind. Now, over here you would have seen also it says cooling tower. Okay, does anyone know what is a cooling tower? Any of you? What is happening over here? The water is getting, it's steam, no? Is running the turbine, but it's still, the water is very hot. Okay, so you'll need to cool it down, okay, before you can put it back here, right? And so because otherwise I'll continuously be generating heat and the whole thing will burst. Okay, so obviously I'll need to control, the temperature which is my inlet temperature into the reactor. So this hot water, I'll need to cool it down, and you can see it is cooled down to about 25 degrees centigrade, 35 degrees, thereabouts. Okay, so so there has to be a cooling process. Okay, now how would you normally cool water?
Using refrigeration.
Yeah, you can put it in the fridge, no? It gets cool, becomes cold water. Okay, but obviously, what is the penalty? There's a high power cost, right?
Yes,
Taking
sir.
the
Yeah,
cooling
and also you see it takes time to cool it down. It's not an instantaneous cooling. Okay, But the bigger problem, the real problem is that it takes a lot of energy. Okay, so what you have is what are known as cooling towers. Now you may have seen these kinds of things in various places in Bombay. These are cooling towers, and you'll see something white coming out. This white is nothing but actually condensed vapor. Vapors of water. Which have condensed. Right? It came out as a vapor and it cooled and got condensed. So it looks like a cloud. And so there's nothing to get scared of. Okay, so it's mainly vapors. Okay, now typically the way you cool, all right, and this is the kind of principles that you must learn while you are looking at renewable energy sources, to how to do things cleverly. Okay, so I need to cool my hot water. Okay, so what is done is that it is fed into these cooling towers, into these huge structures. Okay, so what I normally will do is that I will pour the water from the top. Okay, and so I'll have there's a distributor. I mean, and it uniformly, the water falls from this height, and from the bottom, what I do is that I pass air. Okay, and that air should ideally be reasonably dry air. Okay, now what happens is that air, at a higher temperature can absorb more moisture. Okay, so the humidity, of the air will keep going up, as your temperature goes up. It can absorb more and more water. Okay? So the air, as it is going up, and the water, the hot water, as it is coming down, what will happen is that the air will basically convert some of the water into water vapor, which will get entrained along with my air and come out. Okay, and it's coming out over here, and it's still quite warm. Okay, and the moment it's coming out here, now it sees the cooler environment, the atmosphere. Okay, and so again it will condense, because it will want to reach its new saturation state at a lower temperature, and so you'll get this cloud-like formation. Okay, now can anyone tell me, okay, that's fine, but why did the water cool? Okay. What happens is, now whenever something evaporates, it goes from the liquid state to the gaseous state. What do you need? You need energy.
Yes, sir.
Right. And what is that energy called?
Latent.
Latent.
Right. Latent heat. Okay. I mean, whether I'm boiling the water or whether I'm evaporating at lower temperature, doesn't matter. The moment it goes from the liquid state to the gaseous state, okay, it is a phase change, and we know what is the latent heat. It's 540 kilocalorie per kilogram of water. Okay, so what happens is that, so heat had to be taken, okay, in basically evaporating. Where did the heat come from? That heat came from the rest of the water. Okay, so the water which is falling and which did not become vapor, it is becoming colder, and it became colder because it released its heat to the other water which got vaporized, okay, and in the form of latent heat. Okay, and because latent heat is very substantial, so it leads to a significant reduction in the temperature of this falling water. Okay, and that is what is known as the cooling tower. It cooled down, and that process is basically like an adiabatic process. You understand what is an adiabatic process? Q is equal to 0, right?
Yes, sir.
Right. So if Q is equal to 0, and if some of the Q was required to vaporize the water, then the other part must be minus Q, which means the heat content of the rest of the water must be less. And heat is content is directly related to temperature, so the temperature reduces. Is it clear?
Yes, sir.
Okay, everybody understood now? Good.
Yes.
All right. Now, let us just take a few seconds and just look at the inside of a nuclear reactor. Okay. So what you have, is these things over here are basically your, your you have the fuel assembly. Okay. This is your fuel assembly. Okay, so there are you first have to basically make the fuel. That fuel is typically uranium dioxide. Okay, and that is effectively then encased in ceramic. Some ceramic rods, and that ceramic in turn is again encased in a steel rod. Okay, so there are a huge number of protection which you are putting just so that the radioactive stuff, you're minimizing exposure to radioactivity. Okay, and this is your, your water related flows, your feed water inlet. Okay, and so water is coming from here. Okay, and effectively that is the water which is slowing down the neutrons and also basically getting converted into steam. Okay, and now this reactor, depending on which is the type, over here, this reactor will have these kinds of pressures: 2235, 1050, or 1285. Okay, pressures. Okay, and so this is like an autoclave. All right, at a very high pressure, it is operating. Okay, in these nuclear reactors. Now that thing, whatever I showed you, is basically this thing over here. This is actually not very big, it's quite small. Okay, but the rest of the thing is huge, and the reason is because nuclear energy is all about safety. Okay, you simply cannot afford to have an accident. All right, that's the biggest challenge. Okay, and with all the precautions, we know that there have been accidents. There have been 3 Mile Island, Chernobyl, Fukushima. These have all been major disasters of nuclear reactors. Okay, so it can happen. So what one does is that this, is then housed in a very special concrete casing, and it's massive. Okay, and that concrete housing has to be able to withstand a pressure of something like maybe 8 bar. No, okay, so you can imagine that it has to be designed very, very well. Okay, and the reason is that in case there is any kind of explosion or release over here, that this building should be able to contain that explosion. It should not give way. Okay? The second line of safety is that below the nuclear reactor there is something known as a suppression pool, which is like a huge lake. You won't be able to see it, but under the reactor there's a massive pool of water. Okay, and that is known as the torus or suppression pool. So worst scenario, if you need to, you'll just plunge the reactor into the suppression pool, or you can flood the reactor with water from the suppression pool. Okay, and and plus the primary containment, which I talked about, that the fuel is first encased in ceramic, then in metal cladding. So those are all the safety features which are built into a safety nuclear reactor. You see today there are also, especially after 9/11, when people just went, and what did they do? They crashed the plane into the twin towers. you know, and they gave way. Okay, the World Trade Center collapsed. So there's always a fear that what if somebody who's flying or something, comes and crashes into my nuclear reactor? That can happen. There's a lot of terrorism, terrorist activities. That's another thing that you have to look out for. So in the US now, these buildings have to be able to withstand the impact of a commercial plane crashing into it. You know, it should not, nothing should happen to it if it crashes. Okay, so I hope you understand all the safety features, which are built into these things. And the reason why nuclear power plants are so costly, okay, is because of all the safety measures which you require. And second, after the nuclear reaction, as the fuel has got exhausted, it still got residual radioactivity. And how do you manage the residual radioactivity? That again is another huge problem. Where do you store all this waste stuff after the nuclear reaction is over? Okay, so I hope you understand. Now, although we talked about nuclear reactors, and India, had aspired to get something like 30% of its power from nuclear energy, although presently it's just about a couple of percent, 2 to 3%. Okay, so it's way out, in terms of projections and what is the reality. Okay, now another serious concern is that India actually does not have significant amounts of uranium. It just so India has had to sign agreements with other countries, who provide uranium ore to India. Uranium ore or beneficiated ore, to India. One such country is Kazakhstan, which is one of the highest in terms of uranium reserves. They're so India has a tie-up with them. India has tie-ups with Australia, Canada, countries like that. Okay. Now, since we are talking about renewable energy sources, our job is to identify possible sources. Okay. And second, as I told you, please look at nuclear energy as a possible, as really at least the interim, as a renewable source, because otherwise, we'll be in deep trouble. If you ignore it, we could be left absolutely stranded. We may have nothing, but then we will have to look at also the fuel. Okay. Now, this is a good example of how you can think, in a very different way. Okay. So, although, uranium, people will immediately tell you about uranium ores. Okay. Now, one of the ores which contains uranium, but not in very large amounts, something like maybe about 150 to 200 parts per million, but still quite high. It's not small. Okay, is rock phosphate, from which we make our phosphate fertilizers. And because India has a population close to 1.4 billion, our consumption of phosphate fertilizers is very high. Okay, and now when we were doing an analysis of uranium, I mean, there have been similar studies done in many other parts of the world, but for whatever reason in India there's been no study after 1984. And so we wanted to know that where does this uranium which is there in rock phosphate, where does it end up? Where is it going? Okay. Could it be ending up in the fertilizer? Okay. And sure enough, when we analyze the uranium content in our phosphate fertilizers. This is what commercially we apply on the ground in the fields. Okay, and one had to be very careful with this analysis because uh, if you're not careful, people can accuse you of generating incorrect numbers and various things. So we work with various agencies. Like, this is a technique known as laser fluorimetry. This work was done by BRC. Okay, this was done by a government lab in Hyderabad. It's called the Center for Materials Testing. This was done by one of the CSIR labs. Okay, this is it's called ICPMS, and this was done by ONGC XRF. And we wanted to make sure that they give more or less comparable results. I mean, of course, because nobody knew the other's answer. You'll never get the same results. But we wanted to see whether there is at least some correlation. Okay, except for this set of numbers, which basically showed that this instrumental technique is not suitable for this analysis. But for the rest, more or less, there was reasonable agreement. I mean, I wouldn't say exceptional agreement, but reasonable. Okay, and also with the ONGC testing. You can see 104, 114, 117, okay, 52, 43, 55, 56, 40, roughly. Okay, so not so not so off. Okay, I mean, these results, therefore you can more or less assume that they are correct. Okay, now since then, more of these fertilizers have been analyzed, and the tragedy is that in recent years, like 2019 or thereabouts, the uranium levels have gone still higher in some of the fertilizers. Okay, and so nothing has improved. If anything, things have become worse, except in one case, and we believe we know why this is low. But in all other cases, the figures are very high. Okay, and on an average, you can work out the figures, and if you express the figures in terms of the nutrient, the actual nutrient, which is there in phosphate fertilizer, which we always measure by P2O5, phosphorus. How much phosphorus? It is measured as P2O5. Okay, so if you take on the basis of per kg P2O5, because these fertilizers have different P2O5 content, so something looks low, but when you normalize it for the P2O5 content, it becomes high. But and in fact, when you do that, you find that these values are all fairly similar, except for one case, 270, 352, 355, 200 almost, 265, 247, 292. So now they are all more or less clustered in some way. Okay. Now, if you take the average of that, it comes to something like 302 ppm with respect to P2O5. That means 302 milligram of uranium per kilogram of P2O5. Okay, that is what ppm means, right? Now, what is the consumption of fertilizer in India? This is the figure from, I think, this year, yeah, 2021. Okay, 6.9 million metric ton is P2O5, not the actual fertilizer. Actual fertilizer amount is much higher. This is expressed in terms of only the active constituent, P2O5. Okay, so now if you multiply this figure with this figure, then that is the total amount of uranium which is going into our agricultural fields. Okay, you can multiply it. 6.9 million tons means 6.91 into 10 to the power 6 ton of fertilizer into 302.18 okay, into 10 to the power minus 6 ton per ton of fertilizer. So 302 ppm is 302 ton per ton, right? So I can write it as 302 into 10 to the power minus 6 ton per ton of fertilizer. Now this ton and this ton will cancel out. You'll be just left with the tons of uranium. So it will be 6.91 into 10 to the power 6 into 302.18 into 10 to the power minus 6. This and this will cancel out. If you multiply, it will become 2088.06 ton. Okay, everyone understands the calculation? All clear?
Yes, sir.
Yeah. So now guess what? This is substantially more than India's total requirement for its nuclear power plant. Okay, and not just the ones that are operating now. There are about 7 plants under construction. So when they are also completed, the amount of uranium that we will require total, this amount is actually higher than that. So what it means is that if we could look at phosphate fertilizers or the intermediates from which these phosphate fertilizers are made, if we can look at them as potential raw material for uranium, we are okay. We don't need to go to Kazakhstan then. Okay. But then it's also true that India does not have any reserve of rock phosphate anymore. So we are normally importing these fertilizers or importing the intermediates and raw materials from which those fertilizers are made. So fine, if we do that, we can then extract the uranium before we actually release these fertilizers to the agricultural fields, and so we may have enough for our total nuclear power plants. So I see uranium phosphate fertilizers and the intermediates from which they are derived as possible renewable feedstock, for these things. And why do I say renewable? Because every year we have to apply fertilizer. It's not once in 20 years. Every year. This figure is every year. So every year we will have a supply of uranium. Okay, and so that's really the you need to think about new ways of looking at opportunities. Okay, and I've just tried to present to you one such new way. Yeah.
Sir, you mentioned about phosphate fertilizer and uranium.
Yes.
Uh, there is a problem also associated with the uranium, that the mountain soil is very harmful to the soil. So, can we convert that into energy, isolating from the soil?
It will be too low, the concentrations. Okay. It's just too, because the extraction process will require a lot of effort, and that effort does not get justified if the amounts are very less. Okay. Now let me tell you, there are two issues. One is that up till now, people have tended to believe that all of I don't know if you know, there is a very serious problem of uranium now in our groundwater. Okay.
Yes.
And there is also uranium fluoride, high levels of fluoride in our groundwater, and I'm not going to discuss it, but that fluoride, I believe, is also coming from the phosphate fertilizers. And if there are places like in Punjab, especially in places where there is intense agriculture, there are very high incidence of cancer. Okay, and which somehow there has been it has been attributed to the presence of uranium. Now, up till now, all the people would have you believe that all this uranium is coming from geologic sources, geogenic sources. That is just like you were talking about in the mountains and things like that. But the truth of the matter is that we use so much fertilizer and there is direct evidence of uranium there. I mean, you can't discount it. And that uranium is far more mobile. It just dissolves in water. So, so I think the environmental issues are very serious. One needs to look at, but extracting uranium from very, very weak sources may be extremely difficult. Okay.
Yes, sir. So there are some fungi species also which are used to immobilize uranium.
Very nice, absolutely right. And in fact, you will find that there are, as you said, there are plant species. There are algae, things growing in the sea. Which can actually accumulate. See, this business of accumulation is very interesting. Like a plant is accumulating sunlight, the energy, and converting it into such a beautiful usable form like an oil, concentrated energy. And similarly you have got things which can accumulate even elements, okay, trace elements which are present in ppm levels or ppb levels sometimes, but you find them quite abundant in the biomass, like bromine. For example, in seawater, bromine amount is quite low, but there are many plants which are quite rich in bromine. You've got high levels of bromine. Okay? So this whole process of accumulation by plants is an extremely interesting phenomenon. Okay.
Sir. Thank you, sir.
Now, there are other interesting things that have happened, but this is only something which happened in a temporary way. What happened was that, after the end of the Cold War, when the Americans and the Soviet Union were no longer enemies, what they decided was to dismantle their nuclear weapons. Okay, not all of it, but a part of it. And so when they started dismantling, they said, what can we do with these weapons? And the obvious thing was that why not use this uranium now as the source of uranium for the nuclear reactors? Okay, and now Russia as such does not have too many nuclear power plants, so they actually gave to the United States, over something like a 20-year period, they gave 20% enriched uranium, and this was then basically converted into a more dilute form of the uranium for nuclear reactors, and so quite a bit of uranium has actually got converted from weapons into nuclear energy. Okay, and so I mean it's quite interesting, and in fact they dismantled something like 7,000 nuclear warheads, up till now, to basically convert it into low-grade uranium. I mean, the irony is the amount of time and money that they spent in enriching it to 20%, and then they had to again dilute it, and come back to the typical 3% uranium-235, which is required. So this has been another. I mean, so any country which has got nuclear weapons and it's trying to dismantle them, you could actually use it as a source of renewable energy, source of nuclear energy. Okay? Now, okay. Now, just to tell you again that what is India's ambition. Okay, that it wants to have an installed capacity of something like 14.6 gigawatt electrical by 2024, and by 2050, it wants to source something like 25% of its power from nuclear power. Okay, now this will require a massive expansion, of our nuclear infrastructure in our country. And whether at the end, because nuclear also has its downside of safety, there are concerns. Okay, but I'll tell you how some of those concerns are being addressed. Okay, and India has a very, very strong relationship, for example, has had with Russia. Russia is actually constructing a lot of our nuclear power plants, in our country. So there's a lot of cooperation and collaboration which takes place in this area. Okay. Now let's look at the hazards. Now actually there's Fukushima. I should have put Fukushima here, but there were major accidents. Okay. The 3 Mile Island in 1979 was one of the worst. In fact, I was not aware, and I was actually traveling through that area that day, going from Princeton to Pittsburgh, and our car got diverted, and we had no idea what was happening. They said, "Don't come anywhere near this." And then later on, I found out that the 3 Mile Island accident actually took place at that time. Okay, but what it did was that there was a complete 50% meltdown of the core. That you've seen that vessel and everything. Okay, it got damaged. Okay, and in Chernobyl, okay, there were other reasons for their nuclear reactor is of a different design. And one of the biggest problems was that they use graphite, in their reactors, and that graphite caught fire. Okay, and there were several other things, but let's not go into those details of what exactly happened. But we have to understand that nuclear power has a risk associated with it, and that's why a lot of people don't want it. Okay, but we do not actually have much of a choice. I mean, we will have to go for nuclear, at least as a stopgap measure. Maybe for the next 50 years or so, it will have to be something that India puts in a lot of effort in, and you can see that the country is actually looking at that kind of a strategy. Okay. Now, but at the same time, people are also looking at how to make nuclear energy much safer, not only safer, also much less costly. These power plants, to build, they're very, very costly, extremely costly. Okay. And so, in fact, just to give you an idea of the kinds of projects, which let's say the US Department of Energy, they put out this in their website, and anyone can apply. And if you have a good idea, you can maybe get a project. Okay, and it's called Meitner. Actually, it is after Lise Meitner we talked about, but over here Meitner means Modeling Enhanced Innovations, Trailblazing Nuclear Energy Reinvigoration. Okay, and it says something interesting here, so let me read it out. Nuclear power provides about 1/5 of US electricity generation, delivering reliable, low-emission baseload power to the grid. These plants are all conventional light water reactors, the technology of which has evolved steadily over time. As utilities have begun retiring old plants, however, comparatively high costs have made it difficult to justify building new nuclear plants. So if you want to replace the old plants which are being retired with new ones, today the cost is phenomenal. Okay, so people are getting a bit scared to build those reactors. The low volume of new plant construction combined with expected retirements of existing plants, is projected to reduce US nuclear electricity capacity by 20.8 gigawatt by 2050. So the amount of reduction that they had projected is much more than what we are going to actually have as a total capacity of around 14 gigawatt. So obviously, because they are heavily dependent on nuclear power. Okay, for nuclear energy to contribute in the coming decades, the next generation of nuclear reactor plants need to simultaneously achieve walkaway safe and secure operation, extremely low construction capital costs, and dramatically shorter construction and commissioning times than currently available plants. I mean, because today, it takes 10, 12 years to build a plant, and the amount of money, your capital that is tied up is huge. Okay, so to attain these goals, new innovative enabling technologies for advanced reactor designs are needed. The development of these enabling technologies requires an understanding of the interrelatedness of design choices. Thus, Meitner encourages a rethinking of how pieces of nuclear reactor system fit together when developing the technologies that will make these plants viable. In the building phase, cost savings may be realized through modular and advanced manufacturing techniques that bring most of the work to the factory instead to the construction site. So it's not very different, like say today when we make our flyovers, most of the things are coming assembled, or they're being made in the factories. Then they're being brought, and you're putting together the flyover. All of you have seen how flyovers are being made. Okay, so similar kind of concept is being also looked at for nuclear power plants. Okay, technologies that could reduce operational expenses, including robotics, sophisticated sensing, model-based fault detection, and secure networks to enable substantially autonomous controls, as well as a high degree of passive safety. Passive safety is what you'll always have in a nuclear reactor. Passive safety means foolproof. Even if things go wrong, the hazard will be contained. Okay, that's what passive safety means. Okay, so nuclear power plants of the future. The countries of the world are each planning their own course of nuclear plant development or decline. Nuclear power is competitive with natural gas, absolutely. It does not contribute to global warming. Obtaining the fuel only takes 5% of the energy output. We have seen that 20:1 ratio, okay, of energy output to input. Newer designs are being sought to make them more economical and safer, including small underground nuclear reactors. Disposal of high-level radioactive waste, still an area of concern. Deep burial may be the best solution. But then, whether it will in any way damage, let's say, our groundwater resources, we don't know. There could be things that one will have to look at. But let me tell you, you can see, these are fairly recent articles. March 5th, 2020. The case for making tiny nuclear reactors. Okay, and who are doing this? The biggest companies in the world, General Electric. Okay, and the kinds of plants that people are now conceiving, they're saying, forget about these large plants. Let us make small plants. Small plants means less than 300 megawatt per plant, compared to 5,000, 10,000, 20,000 megawatt plants. Okay, so we're talking about much smaller plants, and also they will be built underground. Okay, and by building them underground, of course, the idea is that you will have an extra safety, that things will not come above ground in case of an accident. Okay, so these are the kinds of things that are going on. Now, let me also tell you about another plan that India has, because India does not have uranium. Okay, so few things that are being looked at. Now, this is over here, the first two equations are basically natural radioactivity. How uranium-238 and how uranium-235 decay. These decays take place over a long period of time. That's not what we are talking about in a nuclear reactor. Okay. Induced radioactivity. This is what we discussed up till now. Uranium-231, 235 being struck by neutron, splitting up into barium and krypton, okay, releasing more neutrons, and this goes on. But you must understand that there are 25 different elements which actually can form from fission. This is not the only pair. There are many other pairs of fission products which can form. Now, this is another thing which you need to understand, that we talked about that uranium-235 is the actual fissile material, but then even if you've got 3% uranium-235, there is about 97% is uranium-238. The question is that what exactly does uranium 238 do? Is it just a passive bystander that is just sitting there doing nothing, or can it in any way adversely affect the performance of the nuclear reactor? So that's the question. Now, what has been found, through very detailed studies which were carried out over many years since the early 1940s, is that the reason why you need to slow down the uranium, the neutron, okay, this is the neutron energy, okay, so here you're going down in energy, here you're going up in energy, okay. So you can see this is neutron energy, and when we say neutron energy, it is basically the velocity of the neutron, okay. Now what happens is that when you slow down the neutron, the cross section of the reaction with uranium-235 becomes much higher, So this is that green, you can see what happens, and this is a logarithmic scale. 1000 over here it is 0.01. So if the neutron is very fast, it's not going to strike and carry out any fission of uranium-235. Okay, just note this. On the other hand, when the neutron is very fast, exactly after, for example, after a fission, the type of neutrons that are released, is very fast neutron. Okay. Now that neutron actually can go and bombard uranium-238 and promote these kinds of reactions. Okay. It leads to ultimately formation of plutonium, and from plutonium you can again get uranium-235. Okay. So but this process is fairly long process. You can see it's 24,000 years to make uranium-235. Okay, so what happens is that this can actually do harm if you have got too much of uranium-238, or if you look at it positively, you might be able to form this stuff, plutonium, and plutonium is also radioactive. I mean, you can actually carry out nuclear reactions with plutonium. Okay, so India is actually looking at that. Okay, and the way you do that is by what is known as the fast breeder reactor. Okay, so effectively what you do is that you don't use water in this system. We talked about water, okay, because water will slow down the neutrons. So what you do is that you have liquid sodium. Liquid sodium is what is actually taking up the heat from the neutron, okay, and you're not slowing it down with the help of water. So that's the first thing to remember. So no moderators are allowed, no water, must use liquid sodium coolant. Okay, and what then it does is that those fast neutrons, okay, can basically react with uranium-238 and produce plutonium, and plutonium can be used as a fuel. Okay, And so, this is something that people are looking at. But there's one more catch, that in this kind of a process, you cannot use that 3% uranium, 3% uranium 235. It has to be enriched to between 15 and 30%. Okay. Now, the problem is, the moment you are at this kind of a concentration, you actually are making weapons grade uranium. So there is always a worry that what if people are using it to make nuclear weapons? Okay, so there's a lot of fear behind using this kind of a fast breeder technology, and the people up till now who have been doing it quite effectively are people in France. So France has been operating fast breeder reactors and generating some of their power. Okay, but India has made the fast breeder reactor. This is a prototype reactor, in Tamil Nadu, Kalpakkam. Okay, and so we know how to make a fast breeder reactor. We will have to see whether we want to go down that line. Okay, now there's another way of doing breeding. Okay, and that is makes use of a resource that we have in plenty. Okay, and what we have is thorium. Okay, thorium is found in a kind of sand. It's known as monazite sand. Typically in Odisha, you get a high amount of monazite sand. Okay, and India is the fourth largest in terms of resources. The amount of thorium resources, we are at about 12% of the world's resources. We have seen now, when we were talking about fossil fuel, everything, we are very poor. Uranium, we are very poor in those resources. But this is one resource that we are good at. So this is the direction in which India actually needs to go, so that it can make use of its own thorium resources. What it does is that the thorium is directly not a fissile material. Okay, but the thorium can react with a neutron, get converted into thorium 233. Okay, that releases a beta radiation from which you can get protactinium. That releases another beta radiation, and this material, artificial uranium, uranium 233, is fissile. This is a fuel. Okay, this is not a fuel. It needs to be activated. So in fact, the the chairman of our Atomic Energy Commission, he had said that thorium is like wet wood. It needs to be turned into fissile uranium, just as wet wood needs to be dried in a furnace before you can burn it. I can't burn wet wood, I'll have to dry it, right? So similarly, I have to treat thorium, convert it into uranium 233, and then of course, one can make use of thorium. Okay, and so this is an area that India is looking at very carefully, and not just India. Look at this, 9th September 2021. China prepares, and it's an article in Nature, China prepares to test thorium-fueled nuclear reactor. Okay, and this is the test, which has come closest to setting up a commercial plant based on thorium. So, China has really taken the lead and gone ahead of everybody else. And although I think India was earlier than China in starting the thorium-based work, but these people are increasingly, it's looking likely that they will be able to make a thorium-based nuclear power plant. Okay, and India must do the same, because we have got the resource. So when you have got the resource, make use of the resource. Okay, now we are through with the fissile, nuclear fission. Okay, now what we'll do is that we will talk about nuclear fusion. Okay, and what did we say? Nuclear fusion is what basically powers the sun. The sun derives all its energy from nuclear fusion. Okay? And every other form of energy is in turn derived from that energy. Okay? And, just like we said once before, the most stable nucleus in our planet is iron 56. Okay, this is the element with this atomic weight 56, which is the most stable, and everything on either side of it is less stable. Okay, now what the sun does is really this. It takes hydrogen, okay, and it gets converted into helium. Okay, this is also helium. This is helium-3, helium-4. Okay, and what happens, you can see, is that the binding energy per nucleon, means per these particles in the nucleus, increases substantially when you go from hydrogen to helium. Okay, now, so what it means is that obviously when something is more stable, it becomes stable by releasing energy, right? And that is the energy, which you have the potential to harness, and which the sun harnesses. The sun basically converts hydrogen into helium, and because it has got a much higher binding energy, so it must be releasing energy, and that is the energy that is powering the sun. Okay, now you'll also notice that there are different types of hydrogen. This is our regular hydrogen, okay, this is deuterium, and this is tritium. Okay, so all of them can give you helium, but we will have to see which is the ones which are most attractive out of these three. Everybody clear? Has everybody understood?
Yes, sir.
Okay. Okay. So now let us try and understand, this nuclear fusion, what exactly it has to do. One is that, imagine it's taking place in the sun, okay, and it's at a very high temperature. You're talking about millions of degrees Kelvin temperature. Now, under those temperatures, an atom will never remain as an atom. Okay, the electrons will get stripped off from that atom, and what you will generate is what we know as plasma state. Okay, so plasma are basically charge forms, of these atoms. Okay, and so it is when these binding are taking place, let's say between two hydrogens, it is not taking place between atomic material, but between these plasma. Okay, so this whole thing is all about nuclear fusion in a plasma. Now, this plot over here basically tells you what is the probability of a reaction happening, this nuclear fusion reaction. So the probability, obviously, if it is 10 to the power minus 21, it means that it is a million times more probable than 10 to the power minus 27. Okay, so this is the probability of this reaction taking place. Now, what else? What will that probability depend on? One is that it depends on the plasma density. That means, obviously, because unless you have squeezed these plasma, these ions, so close together that they come within fusion distance, and that it has to penetrate into all the through all the orbitals of the atom, and it has to basically come right next to each other, the nucleus, and they have got to be at that nuclear distances. The only way to achieve that is if you can increase the density of the plasma to that level, where these nuclei are bang next to each other. Okay. The second is that there is a high activation energy that is required for this process. And so the plasma temperature is a very, very crucial thing. You know? So just to give you an idea, you can see this axis is billion degree Kelvin. Okay, billion. Right. Now, what you can see is that as you increase the temperature, the reactivity is going up. Okay, it's much less here and it's higher as you increase the temperature. Second, what you can see over here is that if you can carry out the reaction between deuterium and tritium, okay, you can actually do it at a relatively lower temperature. When we say relatively lower, it means around 100 million degrees, you know, thereabouts. Okay, and if you were to try to do it with, let's say, deuterium and deuterium, you know, you are talking about a billion degrees or higher temperature, and it is next to impossible, you know, to reach those kinds of temperatures on Earth. Okay, but I can tell you that temperatures in this range have already been reached. Okay, now what is happening when you have fusion? So you have got two of these things coming together. Like, let's say if I take a deuterium and a tritium, you know, so this one, okay, this one. This is difficult to do, but this is the way one will have to do it, you know, deuterium and tritium. So I've got a deuterium and I've got a tritium, okay. They're coming together, they're getting fused, okay, and you are releasing one neutron and you're generating helium, okay. And remember the article, How the Sun Shines. Okay, so that's basically what it is. Now, this stuff over here is coming out with an energy of 14.1 million electron volts, and this stuff is the helium, which is coming out with an energy of 3.5 million electron volts. So most of the energy is in the neutron. But the energy in the neutron is actually going to be required because another neutron has to hit this. So, you know, I need a neutron. Okay. Now, not here, but I'll tell you where the neutron is required. Not for this reaction. This reaction is producing a neutron, but there is a reaction which will consume the neutron. Okay. We will discuss that. So, among these three, you know, the one that is looking most promising is basically the deuterium-tritium reaction, where it's, if I'm around here, I'm at about 100 million degree temperature. Now the question is whether I can satisfy these other requirements of a very high plasma density and keeping it anything, you know, it takes some time to react. So I need to keep it confined at that kind of a density and temperature for a certain length of time. Without that, it will never fuse. Okay. So, time becomes another variable. And so this is known as the triple product. Three things which ultimately control with what ease nuclear fusion can take place. It is the product of the plasma density multiplied by the plasma temperature multiplied by the time that the plasma can be held under the optimum temperature and density. Okay, now this, you know, has been a unimaginably active area of work in the world, right? Because people have realized that ultimately, if we are going to be able to get energy, sufficient amount of energy, this is probably the best chance of getting it. In other words, trying to make an artificial sun on Earth. That's effectively what people are trying to do. Now, there are two ways in which they are looking at it. One is that I told you about this plasma. Okay. Now, this plasma, what I have to do is that I have to squeeze it, as I said, at a very high density. Now, when I've got a material, I require a temperature of 100 million degree. There is no material that is known. It's not like ceramic or steel or anything will vaporize. There's no material which can hold a plasma. Okay. So the way you have to hold a plasma is that it is done through what is known as a magnetic confinement, that there are magnets, placed around the reactor, and what that magnet does is that it repels, the plasma. Okay, so it will never come close to any material. The plasma will just be as if it is being held in the air, but it's not air, because no material can hold it. Okay, so that is known as magnetic confinement. The second that people are looking at is actually making an ultra cold deuterium tritium, which will at a certain point that I can convert it into a solid, okay, and I can make it in the form of a pellet. Okay, so it's a solid pellet. Okay. Now, what I do is that I bombard this pellet with massive amounts of energy. That energy must strike within milliseconds, or less time, microseconds, or maybe shorter, nanosecond. And what happens is, that we all suffer from inertia. Okay, so when you do an action, for me to actually respond to that action, it can take time. That is inertia. Okay, now so I have heated it up with massive amounts of energy, but because the pellet has an inertia, it cannot move. It's like frozen, and so the heat and the energy will go into that pellet, okay, before that pellet can disintegrate. And the idea is that the nuclear fusion will take place in that pellet, inside that pellet, before it can even act. And so that is known as inertial method of inducing fusion. So one is magnetic confinement, the other is inertia. Okay, now, and as I told you, in the last 10 years, it is simply amazing, the kind of progress that has been made. These people have approached this from that fuel pellet thing. They are making a pellet of the hydrogen, and then they are, believe it or not, there are 160 of the highest powered lasers in the world, which at one time, at the same second, okay, they are going and hitting that pellet. Okay, and it's creating massive amounts of energies in a tiny amount of space. Okay, and that is what is inducing the fusion. So these people in 2013, they claimed that they were able to release more energy from this pellet than the amount of energy that went into the pellet from the lasers. Okay, but the experiments were done at a very small scale, and so it was very difficult to judge exactly what happened. Okay, but let me show you something more recent. Okay, 18th August 2021. Okay, and this is just a this is not a real this thing. It's only a artwork, of the pellet. Okay, and there are something like 192 beams from laser. 192 of these things are going and striking this. Okay, and I mean that amount of energy you cannot even imagine that is falling on a pellet. Okay, now let me read out to you just so that you understand what has happened. A US Science Institute is on the verge of achieving a long-standing goal in nuclear fusion research. The National Ignition Facility uses a powerful laser to heat and compress hydrogen fuel, initiating fusion. An experiment suggests the goal of ignition, what is meant by ignition, that I must be able to produce more energy than what I put in. Okay, then I've got a spontaneous ignition. Otherwise, I don't have ignition. It will be self-limiting. Okay, an experiment suggests the goal of ignition, where the energy released by the fusion exceeds that delivered by the laser, is now within touching distance. Harnessing fusion, the process that powers the sun, could provide a limitless clean energy source. In a process called inertial confinement fusion, 192 beams from NIF's laser, the highest energy example in the world, are directed towards a peppercorn-sized capsule containing deuterium and tritium, which are different forms of the element hydrogen. This compresses the fuel to 100 times the density of lead and heats it to 100 million degrees Celsius, hotter than the center of the sun. These conditions help kickstart thermonuclear fusion. Now, an experiment carried out on 8th August, okay, and this is 18th August, within 10 days they have reported it, yielded 1.35 megajoules of energy, around 70% of the laser energy delivered to the fuel capsule. In other words, you can imagine something like 1.9 megajoule of energy was focused on a tiny pellet. Okay, and out of that 1.35 megajoule of energy they were able to extract because of fusion. Okay? Reaching ignition means getting a fusion yield that's greater than the 1.9 megajoule put in by the laser. This is a huge advance for fusion and for the entire fusion community. Debbie Callahan, a physicist at the Lawrence Livermore National Laboratory, which hosts NIF, told BBC News. As a measure of progress, now this is the yield from this month's experiment. It is 8 times NIF's previous record established in spring 2021 and 25 times the yield from experiments carried out in 2018. In other words, in 3 years, they have improved the performance by 25 times, but they have still not reached the ignition point. Okay, but you can understand the pace of improvement in energy output has been rapid, suggesting we may soon reach more energy milestones, such as exceeding the energy input from the lasers used to kickstart the process. Okay, that's what is being done, and I hope you can understand, the kind of phenomenal, activity that is going on. Now, let us again look. This is the one where people are betting more on, which is the plasma, which is confined in a magnetic field. Now, in fact, it so happens that the place where I did my PhD were the people who put up the first such reactor in Princeton. That was in 1976. Okay, and but even now, 76 means what? At that time, I used to hear that by maybe 2050, They used to say by 75 years. By 2050, that nuclear fusion will become a reality, but it's moving down that line, not necessarily by those guys, but by other people, but it's moving extremely fast. Now, let me show you how fast it's moving. In that other, the plasma related, magnetically confined plasma, what is the progress? This 2016, Germany's nuclear fusion machine managed to heat hydrogen gas to 80 million degrees Celsius and sustain a cloud of hydrogen plasma for a quarter of a second. What did we say? Triple product. I need high density, I need high temperature, I need long time. Okay? They achieved high temperature, but they did not achieve long time. Okay? And nor did they achieve, because they didn't have a long time, they didn't also achieve this high density. Now, then came China, right? They set up a plant, these are known as the tokamak, okay? And they were able to, they did not achieve 80 million degrees, but they achieved 50 million degrees. But they could hold on to that temperature for 102 seconds from a quarter second. So, I mean, it was a breakthrough, and this was in 2016. Okay. Now, note these two figures: 80 million degrees in one experiment, 102 seconds with 50 million degrees. And look what the Chinese have done now. Okay. And over here, China's advanced artificial sun fusion reactor just broke a new world record. 3rd June 2021. I'm talking to you about things as they are happening. Okay? And that's the reason why you cannot necessarily get all this information from books, because you'll have to, keep up with the literature as it is happening. Okay? And look what it says. On Friday, the Chinese Academy, China has achieved a new milestone in humanity's experiments to harness the power of the stars. On Friday, the Chinese Academy of Sciences fusion machine reached 120 million degrees Celsius and clung on to this for 101 seconds. In other words, they were able to stick to this time, and they could increase the temperature from 50 to 120. Okay. And if you look at the German thing, what they improved from 80 to 120, and from quarter of a second to 120 seconds. It's just phenomenal. Okay. So it's moving with lightning speed. Okay. The activities in this thing. Okay. And by the way, this is, it's an illustration of how exactly confinement takes place in a magnetic field. Okay. And so this is where it's getting confined, and it doesn't touch anything. It's just magnetic fields are so powerful, that it just stays confined. Okay. Now, look at this. 9 September. Today is what? 16th, right? 1 week ago. All right. And who is partnering with them? Bill Gates. All right. Now, you can imagine that for magnetic confinement, I need massive magnets. Okay. And these are superconducting magnets. Now, typically up till now, magnets become superconducting. Okay. And, when you have, when you reach temperatures of something like 4 degree Kelvin, okay, almost like absolute zero. Okay. But now, of course, about 30 years back, there was a major discovery that you can get superconductivity at much higher temperatures, almost at liquid nitrogen temperatures. You can make things superconducting. So what this MIT startup, along with Bill Gates, these people have done is that they have been able to make the magnet, for the tokamak, which is now a high temperature superconducting magnet. Okay, and so and what it does is that I think it has cut down the energy inputs by maybe more than a factor of 100. And so, it's a spectacular achievement. Okay, but all I'm trying to tell you is that please note that the world might actually be driven by nuclear fusion 50 years from now. All right, and you are seeing these things as they're happening. Okay, it will easily take another 15 to 20 years before any of these things get commercialized, right? But I hope you understand the frenetic pace at which things are happening. Okay? Now, this, of course, is what everybody is banking on. This will be an actual fusion power plant. It is being constructed in France, okay, and there are I think about 20 players, 20 different countries, maybe less, and India is one partner. There are consortiums, so India actually puts in some money, as well as some components of the plant are being manufactured in India, and they're saying between 2025 and 2030, give it about 10 years, and look at the cost, $21 billion. Would anyone put in this kind of money unless, you knew that you are really going after something big, very big, which can solve the world's energy problem for eternity? That's the kind of thing you're looking at. Okay, so keep this in mind. Now, but there are problems. Okay, so what all the people in the world are looking at is the deuterium-tritium reaction. As I told you, it produces helium and releases a neutron. Now, what does a neutron do? Now, I need to have tritium. Okay, tritium is not available. You have deuterium, but tritium is next to impossible to get. All right, so I need to continuously pump in, all right, or generate tritium. And once these plants are running, I can't keep feeding tritium from outside. So the way it is being looked at is that there is a nuclear reaction, neutron plus lithium, okay, produces helium plus tritium. Okay, this is the tritium that will come here. So you can see there is a blanket of lithium, and that blanket of lithium is being struck by the neutrons being generated from this reaction. Okay, and that in turn is producing tritium. So I don't have actually surplus neutrons because that neutron is required for this process. So the energy that I'm getting out is really the energy, that 3.5 MeV, which was there in the helium, over here. And likewise, I'll get energy also from this process. So these will be the two which will supply energy. Okay, but the problem is, where will you get lithium? There's already a shortage of lithium, which people are talking about with the huge introduction of the lithium-ion battery. There are big projects now in how, once your battery goes dead, how to recover the lithium. One of the big problems with the Taliban coming into Afghanistan was had a great source of lithium, and India was eyeing that lithium source. We have a source in Leh, but that's a very small source. But Afghanistan is rich in lithium. The whole world was basically eyeing their reserves, of lithium. Okay, And there is a problem that you may do all this nuclear stuff, everything. And but you may get stuck because you don't have lithium. Okay. Now, the interesting thing is that there is a small amount of lithium in seawater, but ever so tiny. All right. So one of the future areas, which the whole world will need to look at, and India will be in a good position because we have got a long coastline, is that can we recover lithium from the sea, from seawater? If we can do it, then we would have solved this problem. Okay. And, and if not, then you've got a great technology, but you'll be starved for lithium. Unless some new way comes out to make tritium, we'll be all in a soup. All of this investment might go down the drain. So if any of you are looking like, oh, I want to work on a great problem on renewable energy, go and try to extract lithium from the sea. See if you can do it. Okay, just so that you have an idea. Okay, now there is always also another concern. Okay, we know that fission generates a lot of radioactivity. There's residual radioactivity. There's a lot of safety issues around if there's a blow up of the nuclear plant. Now, what is the situation with fusion? So let's just read this. The fusion reaction releases neutrons, the energy of which will be used in future power stations to heat water, to heat drive the power plant. Not really, because the neutron will really go into making tritium. The neutrons would be quite dangerous to humans, but when the plant is turned off, the production of neutrons ceases within milliseconds. There's no production of neutrons. It doesn't carry on. There's no chain reaction. The neutron bombardment also affects the vessel itself, and so once the plant is decommissioned, the site will be radioactive. However, the radioactive products are short-lived, 50 to 100 years, compared to the waste from a fission power plant, which can last thousands of years. Also, the radioactivity in a fusion power plant will be confined to the power plant itself. There will not be any waste needing to be transported for disposal, storage, or reprocessing. Okay, so there will be small amounts of problems because of the neutron, but it should be a much safer thing than basically fission. Now, I've just tried to just like we did once before, like let's say, let us try and figure out, how much energy is released in fusion of 1 kg of deuterium nuclei, right? And we have seen that the helium is coming out at 3.27 MeV. I have not taken the energy of the neutron, assuming that it is going to go and get consumed by the lithium to produce tritium. Although I have not taken into account the neutron that will be released from that process. But then that neutron will again, you see, look at the beauty. Look at the beauty of this whole thing. And one neutron is being produced, one neutron is being captured. So there is no neutron excess that you have in the system. And you're generating this 3.27 MeV, okay, million electron volts. So now you need 2 of this deuterium. I've done this for deuterium, not for deuterium tritium, but you could have done it for deuterium tritium also. Okay, and 1 mole atom of deuterium will have 6.02 into 10 to the power 23, okay, numbers of deuterium, okay, and it will have a weight of 4 total mass, because there are 2 of these deuteriums that you require. Okay, so actually the number of encounters will be 6.02 into 10 to the power 23. Okay, into 10 to the power 3, because I've asked for per kilogram, whereas that is gram atom for this. So into 10 to the power 3 to account for the kilogram, divided by 4 grams, which is the 4 gram atoms for this. Okay, so and then I multiply by 3.27 into 1.6 million electron volts multiplied by 1.6 into 10 to the power minus 19. Okay, and you can work out that this energy will come to about 7.87 into 10 to the power 13. At the break, just quickly do a calculation. Okay. Now, I just thought, just so that you understand, so this is 1 kg of deuterium, how much energy it is releasing. 7.87 into 10 to the power 13 joule. Now, I asked how much energy would be released if I burn 1 kg of natural gas. Okay, so it has got a gross calorific value of 42.4 megajoule per kg. I can write it as 4.2 into 10 to the power 7 joule. Okay, so what is my net ratio? 7.87 into 10 to the power 13 divided by 4.2 into 10 to the power 7. Okay, roughly about 2 into 10 to the power 6 times. Okay, both are joules. Okay, in other words, 1 kg of deuterium fusion releases 2 million times as much energy as combustion of 1 kg of natural gas. Okay? I hope you understand why the world is so excited, about nuclear fusion. The next few lectures will be devoted to bioenergy. Okay, and I think probably many of you are from a life sciences background. So some of the things that I may talk about are things that you already know, but since in the class everybody is not familiar with all of this, so I will be covering it. If you already know it, then treat it as a revision. Okay, but I'll try to obviously discuss these with a slightly different perspective, okay, than what you might have been exposed to. Now you can see it's from the International Energy Agency, and that the feeling is that internationally, up to 2023, that bioenergy is going to lead the growth, okay, of all renewables, at least up to 2023. Okay. So that means, in other words, bioenergy, you really cannot just put it aside. For whatever reason, we seem to be not doing that much, with it. But it's of course, in India, poor people in the villages, they use bioenergy all the time. I mean, cow dung, which is used as a fuel. You have twigs, and you see all these people collecting the twigs and taking it home to light their chula. So we use, bioenergy quite a bit, and it's not just about putting it into fancy cars and talking about bioethanol and all. I think that we need to look at this considering the total perspective of India, and our population. And in our population, people use it in a very rudimentary way. Okay, but there's nothing wrong with it. They're getting their energy. They're cooking their food. How can you not think it is important? It is important. Okay? So bear that in mind. Now, since we are talking about bioenergy, what is at the heart of bioenergy? Where is this energy coming from?
Plants, I mean, plant sources carbon.
Right, and yeah, so plant sources. So what about them? Let's for now talk about plant-based energy. Okay, we will talk about the others, but plant-based energy. Where is that energy coming from?
Agriculture and food waste.
True, but I mean, what is the fundamental process that is taking place?
Decomposition of plant species.
Okay, but that is once I've got the energy, then I'm decomposing and extracting it. But what actually gave birth to that energy? Where is it coming from?
So sugarcane biomass.
No, I understand that. That's true. But how is sugarcane biomass generated?
Photosynthesis.
Yes. Yes. Photosynthesis. That is the fundamental process. Okay. And photosynthesis requires what?
Sunlight.
Sunlight.
Sunlight and
Carbon dioxide.
yes, sunlight and carbon dioxide. Of course, it requires also water. Okay. The key inputs are sunlight and carbon dioxide. Okay. I'm not taking things like soil and this, that, there are so many fertilizers, all that is there. But these are the two key inputs, It is sunlight which drives the process and carbon dioxide which is fixed. Okay? That is what is generating biomass. So, so what we need to do is that we need to understand sunlight also. Okay? And carbon dioxide we have understood. We went through in the lectures of what's happening with carbon dioxide in the atmosphere. So you have got an idea that carbon dioxide is actually, if anything, is going up. In that sense, maybe it is favorable for photosynthesis. Okay, and the other input is sunlight. So let us look a little more about what is sunlight, and because it's so fundamental to photosynthesis. Now, what is really happening is that in the sun, okay, the sun, if you look at the external outer part of the sun, which is radiating energy, okay, the temperature, okay, is something like 5,250 degrees centigrade. Okay, and any such body can be, you can treat it like as if it's a black body, which is radiating energy. Okay, and this equation was worked out by Planck, that this is known as the spectral radiance, right? And it's a function of the frequency and the temperature, right? And it's equal to, this is the right hand side, 2h nu cube, where nu is the frequency, divided by c squared, where c is the velocity of light, okay, into 1 upon exponential h nu upon kt. H is the Planck's constant, nu is again the frequency, okay, and k is the Boltzmann constant, and T is the temperature, -1, right? So what it means is that, and spectral radiance is like the, you can think of it as the intensity, of a particular wavelength of light. we know that we have got visible radiation, and typically when you work out this equation, okay, and you can plot irradiance, which is that BV, okay, versus frequency, or alternatively you can work it out as a function of wavelength, where basically frequency and wavelength, as you know, are related by frequency is equal to c upon lambda, where c is the speed of light, okay, 3 into 10 to the power 8 meters per second. That's the velocity of light. So this divided by the wavelength. So if, for example, I've got 400 nanometers, okay, somewhere here, you can see 400 nanometer. So I'll have to just plug in. I'll get frequency will be equal to c divided by in velocity, and this will be 400 nanometer, which will be 400 into 10 to the power -9 meter. Okay, and just work it out. Just see if this frequency you're getting or not. I just calculated it out. C is 3.8 into 10 to the power 8 meter per second.
So 7.5 into 10 raised to 40.
Yeah, so that's what I've written, right? So you're getting it, right? Okay. So I can from this thing, I can for different wavelengths, okay, I can convert it into frequency, okay, and then I will get the intensities, okay, and I'll just plot that intensity or BV as a function of the wavelength, and for a given temperature, all right, and that temperature which I have taken is the temperature at which the sun is emitting the radiation, which is at about 5000 degrees centigrade. Okay. Now, and that is what spectral radiance is. Now, if you do this, for those who are curious, I would be very happy if you can just plot this for different frequencies, get the relative intensities, and see if you are getting this kind of a plot. Okay, the plot should look like this. All right, and this is your electromagnetic spectrum. You understand? This is your ultraviolet region, somewhere here onwards, 300 to the left. Then this part is your visible region, okay, somewhere up to about here. Okay? And over here is your infrared region. Okay? All clear?
Yes, sir.
Okay. Okay. Now, what happens is that the if you were to measure this right at the our upper atmosphere, the uppermost part of the atmosphere, you actually get a actual intensity profile which matches this. And you can see what a great job these people had done of developing this equation. I'm not going into the how that equation is derived, etc. That will go too much into physics, So we're not going to go into that. But when you are actually looking at it, like let's say at sea level, now what you find again is that the trend is similar, but there are certain places where you see breaks. There is no insulation that you see. Okay, the red is what you actually get. Okay, and the reason for that is that there are absorption that takes place because of the atmosphere, because we know in our atmosphere you've got water, you've got water vapor, okay, and so that can absorb radiation, and you can see over here carbon dioxide, okay, and this part there is no spectral radiation because it is getting absorbed by the CO2, and as CO2 is building up in the atmosphere, this is taking up all that radiation, okay, it's absorbing and releasing it as heat because this is the infrared region. Okay, and so this global warming, this heating that's happening and blaming it on CO2, some of it is because of this. Because we know that that all biomass is created by photosynthesis, okay, and so I was just trying to see what is the efficiency, right, of utilizing the energy from the sunlight, So I just thought, let me take a practical example, okay, and basically because of the interest in biofuels and things like that, food and stuff. Now, typically, the figure that has been used, in places which are quite well lit, okay, places like Madhya Pradesh, Rajasthan, Gujarat. I mean, most places in India, but especially these. Typically, what you get is over a day, if you were to average it out, the solar insolation would be something like 600 watt per meter square. Watt is equal to joule per second. So 600 joule per second per meter square. That is the typical insolation, and I mean you get your insolation for how long? I mean in a day, let's say from something like say 8 o'clock to 6 o'clock, or I mean after that it gets very weak. Okay, so I can take 10 hours per day, right? 10 hours per day, right? And I can also convert from from joule into kilocalorie, right? So if I want to do that, I'll divide by 4.2 kilocalorie per joule, right? And now this insulation, and suppose I've got a plant, like I've taken, let's say one of the plants which has been considered a lot for biofuel, Jatropha, okay? It's a plant which typically would cover maybe a width of about 1.5 meters, but I've taken about say 1 meter, roughly. And so if I look at, and typically if you every 6 months, you get a harvest of the seed, and it's from the seed that you get oil. Okay, so like I've tried to see what is the total insulation falling on the plant over 180 days. Okay, so 600 joule per second for 10 hours. Okay, into 3600 second per hour. Okay, and divide by 4.2 kilocalorie per joule, right? And 180 days, let's say it's falling constantly, and you can work out that the figure is around 1 million joule, 1 million kilocalorie, right? 0.9 million kilocalorie, which will be about 3.6 million joules, thereabouts. Okay. Would you like to quickly do this calculation and see if you're getting this figure?
Yes, sir.
Okay. All right. So you can see you're getting this figure. Now, in that 180 days, let's say when I take a harvest, I find that there is 2 kg of seed, okay, which I'm collecting, and it has got something like 35% of oil. So I'm getting about 0.7 kg of oil, and the calorific value of the oil is 9,000 kilocalorie per kilogram. Okay, so if I multiply by 0.7, it comes to 6,300 kilocalorie. Okay, so just see 6,300 divided by this figure into 100 to express it at percent. Are you getting this figure 0.68? Just see.
Yes, sir.
Okay, great. So you're getting it. So, I mean, I know that roughly about 0.7% of the total solar energy which fell on the plant actually got converted into oil. But then, of course, there are many other things which are generating, which are consuming energy. For example, the rest of the seed, which is 1.3 kg, that will have a calorific value of about may not be 9,000, but it will be around maybe around 3,500 kilocalorie per kg. So I can get that 3,000 into 1.3, and then I can add it. Obviously, that will increase this percentage. All right. Then these seeds are actually contained in a shell, and roughly about 2/3 of the weight of the shell or the capsule is the seed, and roughly about 1/3 or 40% is the rest of the material, which is just lignocellulosic material. So that also has a calorific value of around 3,000-4,000 kilocalorie per kg. So I can add it up, and you'll start finding that it'll probably from 0.68. If I add it all up, it'll come to about maybe around 1.5%. Okay, and then of course that's not all. My plant is also growing. There are leaves, there are branches. Okay, all of those things are forming, and all that is lignocellulosic biomass, which is generating energy if I burn it. Okay, so if I add it up, you'll find that actually you'll probably come to a figure of around 4 or 5%. Okay, and that typically is the kind of efficiencies that are reported for photosynthesis. Okay, so and it could have been more, but then what happens is that you see all parts of the spectrum are not useful for the plant. Like this part is not useful for the plant. Infrared radiation, radiation which is closer to the ultraviolet is not useful to the plant. The plant is actually taking only a part of this, whereas what I'm measuring as the total energy of solar insolation is the entire amount. So if you were to take that into account, you'll find that if you only take the useful part of the radiation, maybe that 4-5% might increase to maybe about 15%, 20%, which is not bad. Okay, which is the actual photons which were utilized by the plant. And what did the plant do? It's very interesting. The plant actually took radiation. Can you believe that? Over 180 days, fairly low level of radiation, 600 joules per second. Okay, and it concentrated that, in this seed, okay, and in this oil, right? So a plant, you can view it as a concentrator of solar energy, and whatever we eat, like our food, sugar, things like that, starch, Okay, they're all fairly high calorie things. Okay, and so the plant is really doing that. It's concentrating radiation, through a beautiful process. Okay, and giving it to us in a way that it is much more useful and usable as a fuel, as a source of energy. But I hope you can see the interrelatedness of solar energy and photosynthesis. Okay, now let us look a little more at photosynthesis. Okay, now there are two different types of reactions that actually happen during photosynthesis. Okay, all biologists will know it. Others may or may not know all the details. So I'll cover it. Okay, so one part is actually things which are light dependent. It only happens when there is light. Okay, and so this is called the light dependent reactions. Okay, and then there is another part which is light independent reactions. Okay, these don't need light, they are happening in the dark. Now, what is happening in the light dependent reaction? Effectively, what you can think of is that water is being split and it is getting converted into oxygen. Okay, now, like for example, you know that if you do electrolysis, right, you need energy for that. Okay, and it breaks up into hydrogen and oxygen. Okay, but you need energy. And similarly, even when the plant is breaking up water and forming oxygen, okay, it's a light dependent reaction because it's an uphill reaction. It's thermodynamically unfavorable, this reaction. It is possible only because of the input energy from light. Okay, now what is actually absorbing the light? Well, there are certain enzymes. Okay, and in this particular case, the reaction that actually splits water is a manganese-based enzyme. Manganese is there in the active site. Okay, the main principal harvesting of light is done by chlorophyll, which is a magnesium-containing entity. But the one that is doing the splitting is an enzyme, which is a manganese-based entity. Now, what else is it doing? I mean, it's releasing oxygen, but you see the rest of it, which I couldn't think of as hydrogen, is I can also think of hydrogen H as if it has got an electron with a high energy potential, and I've got proton. Okay, and that electron, which has got a high energy potential, it's something like if I take a molecule and I excite it to the excited state, what happens? The electron goes to the excited state. So the electron is at a higher level. It's still an electron, but it's got a higher energy. Okay. So similarly, I can think of the H part as if it is a H plus and an electron at a higher energy level. Now, one reaction which it does is it converts ADP, this ADP, into ATP. What is ADP? Adenosine diphosphate. We'll look at the structure. Okay, and it combines it with a phosphate group, right, and forms adenosine triphosphate. Now, we will see that this light dependent part is in turn made up of two parts. They are known as photosystem 2 and photosystem 1. I'll discuss this in the subsequent slides. Okay, so it's a little more complex, and one of those photosystems is responsible for converting ADP into ATP, and the other one is responsible for converting NADP into NADPH. Okay, so it's getting reduced. Okay, there is a reduction chemistry taking place. Whereas here, there's no reduction chemistry. It's just a phosphate either combining or getting released in this. Now, both of these are at a higher energy. Okay, so ATP actually is like a storehouse of energy. So the energy from the sun, not only did it split and you got oxygen, it actually converted a low energy substance into a high energy substance, into ATP. Likewise, it converted NADP, which is a low energy substance, into a high energy substance, NADPH. And not only that, this substance is a reducing agent because of the presence of the hydrogen. Okay, so now I've got an energy source, in the form of ATP, and I've got a reducing agent, okay, in the form of NADPH. These are the things that are utilized in the light independent reactions to convert carbon dioxide into all the compounds that we are familiar with, like oil, glucose, sugars, amino acids, which build protein. Okay, so that's what is going on in this basic apparatus, which nature must have evolved over millions of years. It is such a sophisticated apparatus that nobody in the lab has ever been able to make something like this. Okay? It's only nature. Nature has been able to do it. We have not been able to do it. Now, there are some biology terms, and there are terms. I mean, but it's good to be familiar with them. Like the dark reactions, they occur in a part which is known as the stroma. Okay, and the light dependent reactions, this stuff occurs in what are known as the thylakoid membranes. Okay, so that's all. You more or less have got a feel, for what's going on. And by the way, this is the chloroplast. These are the things which are actually harvesting the light and then channeling the light, to the enzyme, which is then splitting water to release oxygen and converting ADP into ATP and NADP into NADPH. Okay? Okay. Now, this is, if you look at the architecture of this photosynthetic apparatus, it's very interesting. The thylakoid membranes, this part, it looks as if it's like carom pieces, okay, as if they are all stacked together. And then you have got a lot of the open regions, which is the stroma, and the stacked regions are known as the grana. Okay, this one. Okay, so this is where your light dependent stuff is taking place, and your other stuff, is taking place. The dark part is taking place in the stroma. Now, let us try and read out their names, and later on, what I'll show is I'll show you their chemical structures. Okay, ADP, adenosine diphosphate, ATP, adenosine triphosphate. So it just has one more phosphate. Okay, and in the process, it goes into a higher energy state. NADP, nicotinamide, adenine, dinucleotide, phosphate. That's what NADP is. In this slide, the CO2, as I told you, you can see that the ATP and the NADPH, which were produced in the light dependent steps, in the light dependent reactions, they are moving towards the stroma, and carbon dioxide is also moving to it. water is there, okay, and you have got an enzyme which is known as Rubisco, okay. Rubisco is ribulose 1,5-bisphosphate carboxylase oxygenase, okay. Now, so this is an enzyme. I mean, don't worry about it, okay. I'll show you broadly what it looks like, okay. And what they do is that they fix the carbon dioxide to form a 3-carbon entity, okay. This is G3P, which is basically glyceraldehyde 3-phosphate, okay, just like glycerol, except that it's got an aldehyde group. You know, one of the OHs got converted into aldehyde and it is phosphated, okay. That is your glyceraldehyde 3-phosphate, G3P. Okay, and so broadly, this is what happens. The man who basically revealed all the reactions that take place in the light independent part is Melvin Calvin. He was at University of California at Berkeley. Okay, he was basically a chemist who later on unraveled this whole mechanism, and he won the Nobel Prize in the 60s. You know, for his work, and this is known as the Calvin cycle.